Uh, Hello. So, welcome to the second session of the problem solving session. So, I hope you can hear and see the screen, right? And please interact through this chat box. Yeah. Okay. It's fine. Okay, then I will start. So, I hope you are already familiar with the concept. So this week's well, yes, welcome to the session. So this week's problem set was based on what is called the Liouville's theorem and the Cauchy integral formula and Cauchy integral theorem. So these two were the most basic concepts. So let's start the first one. So let fz be an entire function such that it has a minimum. So there exists an m greater than 0 such that the modulus of fz has a minimum, like it's always greater than m for any complex number. So we have to show that fz have to be a constant. So like it looks like the inverse of the Liouville's theorem, right? So there, if a function has a maximum in the modulus, so and then if the function is analytic, so the function has to be constant. So it just looks like the same problem, but the maxima is replaced by minima. So yeah, so as I say, so if we take this, if we define this function gz as inverse of fz, so we clearly see that gz will have the maximum in its modulus, right? So if maximum, so if the modulus of fz is greater than m, so obviously, so modulus of gz is less than 1 by m, because it's the inverse of fz. So, and given that fz is an entire function and the modulus of it is greater than a positive number, so we know that if a complex number have to be 0, if a complex number's modulus is 0, then the complex number itself has to be 0. But here, we given in the question is that the modulus of the complex number is always greater than 0. So we see the fz never vanishes on the entire complex plane. In other words, fz has no 0. So since fz is never 0, so since fz is never 0, so gz never diverges to infinity. So of course, so then gz is also an entire function. So gz is analytic through 1. So it has no pole singularities or all that. So gz has no singularity, so gz is an entire function. So what do we have now? So we have gz as an entire function, the modulus of which is bounded. So of course now we will appeal to the Liouville's theorem. So since the entire function gz is bounded, then by Liouville's theorem gz is a constant. So gz, which is the inverse of fz, is a constant. So obviously fz is itself a constant. So yeah, so that was the explanation. Okay. So, do you have any question? Okay, if not, so then let me move on to the second problem. So, yeah, so it's, well, so, I want to ask one thing. So, are you familiar with this maximum modulus principle, or will it be taught in the next week? Because I think in the next problem I will have to use that principle. Okay, so I'll assume you are familiar with maximum modulus principle. Okay, so the problem statement is, so let fz be an entire function. Well, so is the audio problematic? Okay, so let fz be an entire function and D be a open but bounded subset of the whole complex plane. Okay, so we have to show that the image of this subset, which is given by fd. So we have to show that fd is open and bounded, but fd bar is closed. So in the language of set theory, so D bar is called the closure of an open set. So D bar is the closure of the open subset D, and by definition of closure, so D bar is closed and bounded, because so it is closed. So in this context of this complex plane, because D is an open subset, so D bar is closed because it's the closure, and it's also bounded. So yeah, here is another terminology. So if a subset is closed and bounded, so it is called a compact subset. So yeah, so D bar is closed and bounded subset of the whole complex plane. Okay, so now, okay, so we have this property of D bar. Now we have to show if D bar is closed. Okay, so now we'll appeal to the maximum modulus principle. So this principle is valid for an analytic function in a given open subset or domain. So since fz is an entire function, so by maximum modulus principle, this entire function fz cannot take maximum value. Cannot take a maximum value for its modulus in the interior of any domain. So like the maximum value of an analytic function, the maximum value of the modulus of an analytic function has to occur on the boundary of an open subset. So this is called the maximum modulus principle. So it has to occur on the boundary of some domain or open subset. So since D bar is closed and bounded, and so of course since D bar is closed, so it will have a boundary. Thus if D bar, so because it's an entire function, so if D bar will have the maxima in its modulus on the boundary of the of the closed and bounded subset D bar. Okay, so of course since there is a maximum in the modulus of fd bar, so of course fd bar is bounded. So then of course fd bar is bounded, and it is bounded as well as the maximum value of its modulus is attained at some point of the boundary. So the uh, so the maximum value of the modulus with which its modulus is bounded is actually attained at some point of the boundary. So in this sense, FD bar is also closed. So thus we have FD bar as a closed and a bounded set. So then our next assignment is to show that FD is open and bounded. So we just have showed that FD bar is closed and bounded. Now we have to show FD is open and bounded. So we'll all know that. So D bar is the closure of D. So by definition, so D is the subset of D bar. And of course, since F is an entire function, so the images are also the subset of one another. So image of D is the subset of image of D bar. So this is a property of analytic functions. So since FD is the subset of FD bar, so we also have FD as bounded because the set of which it is a subset is itself bounded. So FD better be bounded. And now let us appeal to the maximum modulus principle. So maximum modulus principle says that the maximum modulus of Fz can never be reached at the interior of an open subset. So the maximum modulus of Fz is never reached in D, but it is reached only at the boundary of the open set. So in the interior of this domain D, the maximum modulus of Fz is never actually attained. So in this sense, Fd is an open set because the value with which by which it is limited is never actually attained by this function. So in this sense, Fd is an open set. So this concludes the answer of this question. So yeah, I hope it's clear. Okay. So next, the problem which we will look at. So that is an extension of this problem. So we'll use some properties that we have derived from this question. So yeah, the statement is let Fz be an entire function and again D be a bounded subset of the whole complex plane such that for any complex number that is in this complex plane there exists an element in the D, so which is the bounded subset with this property. So Fz equals to Fz bar. So we have to find which function may have this property. Okay, so for any function, for this function, if we input a number from the domain D, so it will always be equal to some number. Some output that is obtained from the input that lies on the whole complex plane. So it doesn't matter whether Z lies in the interior or the exterior of the bounded region D. Okay. So as we have showed in the previous problem, so Fd is bounded. Okay, because Fz is an entire function and D is a bounded subset, and we just argued in the previous problem that Fd has to be bounded. We don't know now whether Fd is closed or open, but Fd is definitely bounded because of this maximum modulus principle. Okay, so since Fd is bounded, so it does mean that the modulus of Fd has a maximum value. So there exists a positive number such that for any z dash belong to D, the modulus of Fz prime is less than that positive number. Okay, because we just saw that Fd is bounded and Z prime belongs to D. So Fz prime is bounded. So, and by this statement in the question, so Fz equals to Fz bar. So we have for any Z in the complex plane, So of course, then for any z in the complex plane, so mod fz is also bounded by m. So yeah, straightforward logic. So what do we have? So we have an entire function fz whose modulus is bounded. Okay, yeah, whose modulus is bounded. So by Liouville's theorem, the entire function on the whole complex plane fz, which has a maximum modulus, so by Liouville's theorem it better be a constant. So the function fz has to be any constant. So no other possibility is there. So okay, this concludes our third problem. So now, yeah, so this concludes our discussion on the maximum modulus principle and Liouville's theorem. Now we'll move on to complex integration, like contour integration and uh, Cauchy's integral theorem and Cauchy's integral formula. Okay, so let us now calculate this integral. So please look at this integral. So where C, so we have this positively oriented contour integral. So positively oriented means counterclockwise. So our contour is this curve. So this is a closed curve. This is actually an equation of ellipse. So I hope you know that. So ellipse is the locus of a point, so whose distance from two fixed points, I mean the sum of its distance from two fixed points is always constant. So that is an ellipse. So here you see, so if z is a point, so the distance from z, the distance of this point z from point 2 and point minus 2 is equal to 6. Okay, so it's an ellipse. So z can go anywhere with, but have to respect this property. Yes. So now we all know that. So it looks like we have to use the Cauchy's integral theorem or formula, depending on whether z is so whether this I pi by 2 is inside or outside the contour. So if we look at this integrand, we will see that, so of course Ez is an entire, e to the power z is an entire function, so it is everywhere analytic, but there is the denominator, so it is 0 at z equals to I pi by 2. So the integrand has a pole singularity at z equal to I pi by 2. So we have to decide first whether this point of singularity lies inside or outside the contour C. So depending on that, we'll have to use integral theorem or formula. So now one quick check. So I mean, how to check whether a point lies inside or outside a contour. So okay, as I just described, so for any point on the contour, the sum of the distances of that point from 2 and minus 2 is 6. So if z prime is inside the contour, so its distance have to be less than 6. And if it were outside the contour, its distance from these 2 points, so it had to be greater than 6. So for a point inside, we have to satisfy this condition. So, and now we'll check whether z naught lies inside or outside. So for z naught equal to I pi by 2, we can see this distance. So just put z naught equal to I pi by 2 here, and you will find that this distance, the sum of those two distances is less than 6. Yeah, the sum of those two distances is less than 6. So that means this z not equal to I pi by 2 point, it lies inside the contour. Okay. Now we have the singularity of the integrand that lies inside the integration contour. So of course we have to now appeal to the Cauchy's integral formula. Okay, yeah, the point z naught is inside the contour. So now by Cauchy's integral formula, so straightforwardly, we now use the Cauchy integral formula. So 2 pi I into e to the power I pi by 2. So just replace the value of the pole. So this gives us minus 2 pi. So yeah, that is the answer. That is quite straightforward. So in this kind of problems, all we have to do is to find if some point of singularity of integral lies inside or outside the integration contour. So a similar kind of problem. Yes, let's see with a positively oriented ellipse. So it's an ellipse and the function fa be defined like that. So it's the function of a, like you are integrating z here. So at the, of course you know, in the final answer there will be no z dependence, but the final answer will depend on a. So it's a function of a. Okay, so we need to find the value of derivative of this function fa with respect to a at the point a equal to -1. So this is the question. So again, so you see, look at this integrand. So you'll see that the numerator is an entire function because straightforwardly it's a polynomial, and the denominator, yeah, the denominator has a 0 at z equal to a. Okay, so depending on whether a lies inside or outside the contour C, we'll see how to compute this integral. Yeah. If the point A is outside the contour, then the integrand is then analytic in the region enclosed by the contour, of course. So from the Cauchy integral theorem, in that case we have f equal to 0. So if a lies outside the contour, then the integrand is analytic in the region enclosed by the contour. So by Cauchy's integral theorem, f equal to 0. On the other hand, now if the point A is inside C, so you see this point of singularity of integrand now will lie inside the contour. So now we have to use Cauchy integral formula. So just use, it's the simple pole, so straightforward formula, 2 pi I into 4 squared plus a plus 5. So I've just substituted a in the numerator. So, and of course since fa is a polynomial, so it is everywhere differentiable, so no problem with differentiability, continuity, etc. So f dash a is straightforwardly given by this 2 pi I into 8a plus 1. Okay. So now we'll check whether this point a equal to -1 lies inside or outside this given ellipse. So we see a equal to -1 means in our xy coordinate language, so this is the -1, 0 point. So of course this point lies inside the ellipse, because if you substitute it in the equation of ellipse, you will get 1/4, which is less than 1. So it is inside the ellipse. So this implies, yes, since it's less than 1, so the point a equal to -1 is inside the ellipse. So we'll have to use this formula. So this f dash a equals to 2 pi I into 8a plus 1. This formula was valid for any a that was inside the integration contour. So just substitute a equal to -1 there, and you will get -14 pi I. Okay, pretty straightforward problem. Yeah. So is there any question? Okay, I don't think so. So then I'll move on to the next one. So again, complex contour integral given this curve. So this curve, as you recognize, so this curve is a circle. So the center of the circle is at z equal to 1 and the radius of the circle is half. So center at 1 comma 0 and radius is half. So our contour is that circle. So let us look at this integrand. So you see again we have no problem with the numerator, e to the power z is entire function, but in the denominator you see the denominator has several zeros. So like it vanishes in some points. So it has zeros at z equal to 0 and z equal to 1. Okay, so then the integrand is singular at z equals to 0 and z equals to 1. So now again the standard algorithm. So now we have to check if 0 and 1 both lies inside or outside, or I mean where they reside with respect to the contour. So again straightforward check. So if we substitute z equals to 0 in this contour equation, we'll get z minus 1 greater than half. So z equals to 0 lies outside the contour, and z equals to 1, which as I said, which is the center of the circle, of course lies inside the circle. So z equals to 1 lies inside the contour. So the factor of the integrand that is analytic inside the contour is e to the power z by z, because you know z equals to 0 lies outside the contour. So inside the contour, this e to the power z by z is the analytic factor. Now you see z equals to, we have a pole at z equal to 1, but this is not a simple pole, it's a third order pole because it has this power 3. So now the straightforward Cauchy's integral formula is not valid. We have to use a different formula. Yes, we have to use a defined formula. So this formula is given by that. So if the pole is of order n plus 1, so we know that if the point z equals to z naught is enclosed by a counterclockwise contour C, and fz is an analytic function in the region bounded by C, then we have the following formula. So fz is analytic inside the contour, and z equals to z naught is the point of singularity, and it is a n plus 1 order pole. So the answer of the integral is given by this. So 2 pi I, so that factor divided by n factorial, and we have to differentiate fz with respect to z n times, and then substitute z equal to z naught. So this is the formula that we'll have to use here. So okay, and one important thing is that whenever we will be given something like that, like 1 minus z, but here I showed that it was z minus z naught. So the point of the position of the singularity is always at the right hand side of the minus sign. So that is how you have to you have to factor out minus signs and all other numerical factors out of the integrand and bring the integral bring the integrand in this form. So z minus z naught, but here you are given 1 minus z, so you have to bring it like z minus z naught. So that is why I have brought a minus sign here and re-expressed the integrand like this, z into z minus 1 whole cube. So we will always have to do it. So straightforward now. So only z equals to 1 is inside the contour. So e to the power z by z is the analytic factor of the integrand. So by the uh, higher Cauchy integral formula, so this equation 1, so we differentiate it twice at point z equal to 1. So this is twice differentiation, and then substitute z equals to 1 and you will get this answer, minus I pi e. So what is that? So yeah. So the new thing that we have seen in this problem is the use of this higher Cauchy integral formula. So that involves differentiation and the subtlety that if this is given like 1 minus z or z naught minus z, so we'll always have to bring it in the form z minus 1, or more precisely in this form z minus z naught. The point of singularity must lie in the right hand side of the minus sign. So why do we have to do so? So that will be clear when So that will be clear when we will do the series expansion and residue formula. So for now, you just have to trust me. Yeah. So the next problem, so again similar kind of problem, but of course the integrand is different, so is its singularities. So again the contour is same. So now let's look at this integrand. So it has three singularities. So remember, log z is not an entire function. So z equal to 0 is the point of singularity, because log 0 is minus infinity. So we do think like that. So z equals to 0 is a point of singularity, and it's a different singularity than pole singularity. So it is called a branch point singularity. And associated with a branch point is a branch cut. So I don't know if you are familiar with this concept of branch singularities. So are you familiar? Okay. I think this concept has not been introduced right now. Okay, but yeah, in this problem, we don't need to use, much about this branch cut. Just we have to use that log z is singular at z equal to 0, and we see z equals to 0 was outside the contour. Yeah, in the previous problem, we saw that z equal to 0 lies outside the contour. So same contour here. So the branch point singularity of log z lies outside the contour, so no problem. Okay, and then look at this denominator. So z square minus 1. So z square minus 1 vanishes at 2 points, right? So it is at z equal to 1 and z equal to minus 1. So 2 zeros of z square minus 1. So okay. So now so the integrand is singular at z equal to 0 and plus minus 1. Okay. And again we see, so now we will check whether minus 1 lies inside or outside the contour. So if you substitute minus 1 in the equation of contour, you will get that z minus 1 is greater than half. So of course, then z equal to minus 1 lies outside the contour. Okay, so the z equal to minus 1 singularity will not contribute to this contour integral. So only z equal to 1, so which was the center of the circle, lies inside the contour, and all we have to do is to consider the contribution of this pole singularity at z equal to 1. So the factor of the integrand that is analytic inside the contour is log z by z plus 1 whole cube. Okay, so now look at this integrand. Then I have factored out z square minus 1. So the numerator is analytic inside the contour, but the denominator has singularities. And again, so z equal to 1. Okay, the singularity is okay, the singularity is at z equal to 1, and you see it's a third order pole. Okay, it's not a simple pole. So again, we have to use the higher Cauchy integral formula. So all we have to do is to differentiate twice with respect to z, and then put z equal to 1. So just straightforward calculation, and after doing so, you will get this answer, I by 2. So yeah, so from this problem, we again, revise the use of this higher Cauchy integral formula. So yeah, so as you have seen by now, so the most important thing in these problems is to find the location of the point of singularities with respect to the contours. So you do that, and after that it's just just using the standard formula, nothing more. Okay, then we have this problem. So it's a different problem, different kind of problem. So this is a real integration. Real integration means the integration variable is real. So it is varying from 0 to 2 pi, and the integrand, okay, in integrand you have this e to the power I theta, which can be written as cos theta plus I sin theta, and then sine of some complex number, we can always express that as sin x sine of some real part multiplied by sine hyperbolic and cos hyperbolic of the imaginary part. Okay, so yeah, so in this sense, it's a real integral, because as I said, the integration variable is real. So the easiest way to perform these integrals is to substitute e to the power I theta equal to z. So then by this substitution, you convert these real integrals into complex integrals. So e to the power I theta equal to z, so d theta will be dz by iz. So what will be the differential integral measure in the complex case? So this is this d theta equals to dz by iz. So you see e to the power I theta is equal to z. So mod z is equal to 1. So mod z is equal to 1 is the equation of a unit circle with origin as the center. So since mod z is equal to 1 and the integral theta goes from 0 to 2 pi, so the integral theta goes to 0 to 2 pi. So we see after substitution, we have made this real integral into a contour integral over the complex variable z along the circle mod z equal to 1, and in a counterclockwise sense, because in the argand plane, so it is typical to define the angle theta in the counterclockwise sense. So on the real axis, on the positive real axis, so theta equal to 0, and from there if you go in the counterclockwise direction, theta increases until you reach 2 pi, again at the positive real axis. So that is the standard convention. In this sense, so our contour is traced positively. So we have, so this is the integral given in question. So in this second line, so I have converted it into a complex contour integral. So our contour is unit circle, positively oriented unit circle, and here I have substituted d theta with dz plus iz, and here I have substituted e to the power I theta as j. So we have this contour integral dz plus iz sine cube 3z plus pi by 4. So you see, it's straightforward. So sine cube 3z, so sine functions are always, so yeah, sine cube 3z plus pi by 4, it is an entire function, so it has no singularity, and only singularity of the integrand is at z equal to 0, that lies inside the contour. Okay, and it's a simple pole, so all we have to do is to use the Cauchy integral formula. Straightforward, just substitute z equal to 0 in the integral. So we have 2 pi I divided by I, so I and I got cancelled, so 2 pi sine cube 3z plus pi by 4, substitute z equals to 0 here, and you get this answer, pi by root 2. So yeah, that was a pretty easy problem. So it is just one example of using complex integrals, complex contour integrals to evaluate real integrals. So okay, so now we are left with the last problem of the session. So you see, in these problems we have nothing much to do. Okay. So now the final problem. So again, I would like to calculate this real integral. So cos squared 3 theta, 5 minus 4 cos 2 theta, and theta goes to 0 to pi. So this is the real integral, and I would like to use complex analysis to evaluate this integral. And you see 0 to pi. In the previous problem, our limit was 0 to 2 pi. So after substituting e to the power I theta is equal to z, so that was like, so we got the unit circle and we traced over the circle of a full revolution. So because we were going from 0 to 2 pi, so that was a full revolution along the circle. But here you see, if you do the same substitution, you will trace the circle only about the antipodal point. So you will go only up to pi from 0. So that is like tracing the half circle counterclockwise. So let us see if we can somehow trace the full circle. So for that, in this kind of problems, the first thing we will do is to try to convert the limit of the integral to 2 pi. So like we try to do, we would like to see if that can be carried out somehow. So I have defined this integral in the question like I, and using the property of real integrals, so this is the standard property. So this right hand side. So there we get a factor of half, but the limit is changed into 2 pi. So now if we do the substitution, we will see that we can trace the circle one full revolution. I hope this is familiar. This kind of changing of limit. So now all we have to do is to use this identity. So cos n theta is equal to e to the power I n theta plus e to the power minus I n theta divided by 2. And then we will substitute e to the power I theta equal to z. So in this language, so cos n theta is translated into z to the power n plus z to the power minus n by 2. Because you see e to the power I theta is equal to z. So now we will substitute this thing, so cos n theta in terms of z. So we will substitute cos n theta in terms of z in the integrand. And then we will convert this integral into a complex contour integral. Again, since mod z is equal to 1 and in integral 2, theta goes from 0 to 2 pi. So after substitution, we have the contour integral over z along the unit circle in a positive sense, just like in the previous problem. So now we will do the substitution. So this is the real integral, and then we substitute this cos n theta equal to zn plus z to the power minus n by 2. Substitute this, and we also change the integral measure. So d theta was dz by iz. So substitute this and like simplify. So you will get this step, and then we will do the factorization in the denominator. So this is the factorization, and you see, as I said, so you see there is this 2z square minus 1 and there is a minus sign in the front. So as I said, so in this kind of problems we have to always bring the integrand in this form, z minus z naught. So the point of singularity is at the right hand side of the minus sign, and z minus z naught, and there is no coefficient associated with z. So if z has some coefficient like it is here, so you have to factor it out. So I have factored this 2 out. So 8 into 2 is 16 and z square minus half. So from this 2z square minus 1 factor we get this z square minus half, and z square minus 2 is as it is. So this is the complex contour integral we have to finally evaluate. So now again the standard stuff begins. So given this contour unit circle, we have to locate the poles, whether they are inside or outside the contour. So we see where are the singularities. So of course the numerator is again an entire function because it's a polynomial in Z, but the denominator has some zeros, so that is where the integrand is singular. So where are the denominator zeros? Okay. So the denominator is 0 at z equals to 0 because it's z to the power 5 factor. Z equal to plus minus root 2. This is the solution of z square minus 2, and z equal to plus minus 1 by root 2. So this is the solution of z square minus half. So these are the 5 zeros of the denominator. So of course only, so z to the power 5, so z equals to 0 is the fifth order pole, and the other 4 are simple poles like order 1 poles. So now locating the poles. So out of these only the fifth order pole z equal to 0 and the simple poles z equals to plus minus half lie inside the contour mod z equals to 1. So you see, for z equals to plus minus root 2 we have mod z equal to root 2, so which is greater than 1. So z equals to plus minus root 2 lie outside the contour, but z equals to plus minus 1 by root 2 we have mod z equals to 1 by root 2, which is less than 1. So consequently z equals to plus minus 1 by root 2 lies inside the contour, and z equals to 0 is of course the center of the circle. So we have these 3 poles, so z equals to 0 and z equals to plus minus 1 by root 2, that will actually contribute to this complex contour integral. Okay. So now you see, as I said, so z equals to 0 is the fifth order pole, and z equals to plus minus 1 by root 2, those are simple poles like order 1 poles. So now for z equals to 0 we have to use the higher order Cauchy integral formula involving those differentiations. And another thing is that, so there were 3 poles, so we have to simply add the contributions from each of those 3 poles. So that will give us the final answer. So this was our integrand. So first we calculate the contribution of z equal to 0. So it was a fifth order pole, that is why I have used this formula 1 by 4 factorial and fourth order derivative, and then putting z equal to 0, and then the contribution from z equals to minus 1 by root 2, which is a simple pole. So we have to find the value of this factor at z equals to minus 1 by root 2. You see, this whole factor is analytic at z equals to minus 1 by root 2. And similarly for 1 by root 2, which is again a simple pole. We have to just substitute z equals to 1 by root 2 in this factor. So like after doing this quartic order differentiation and substituting those values, we will get 3 pi by 16 as our final answer. So as you see, so yeah, finding the, differentiating 4 times of such kind of integrand is quite difficult and time consuming. So we'll have a better strategy to tackle this kind of problem. So we'll learn those when we do the residue and series expansion. So using series expansion, so we'll see that we can circumvent this differentiating large times by simply a series expansion, and that procedure will not take a lot of time, unlike this one. So yeah, we'll be mostly using those residue formula in future, but for illustration purpose, like how to evaluate real integrals using complex contour integrals, so I have chosen to demonstrate this problem. So yeah, that concludes today's session. So if you have any question, feel free to ask. Well, I guess you have some question. Oh, hi. Uh, yes, what is the problem in problem 5? Okay, yeah, please write your, concern about problem 5. Meanwhile, I discuss another doubt. So, to get no, you get the direction of the curve. As I said, so these are actually the right convention. Like, so on the positive x-axis, so theta 0 is defined on the positive x-axis, and then if you trace the then you trace counterclockwise one full rotation, so you will get from 0 to 2 pi. So this is the convention, like you have to trace counterclockwise to get 0 to 2 pi. And in these problems, I have got 0 to 2 pi. So because you see, so the limit of the integration was theta going to 0 to 2 pi. So like theta, the lower limit of theta was 0 and upper limit was 2 pi. So you have to trace theta from 0 to 2 pi, which amounts to revoluting in counterclockwise direction, because as I said, the unit circle is traced counterclockwise when you go from 0 to 2 pi, and in the limit you are also going from 0 to 2 pi. So that is how we define the direction of the curve. So yeah. And yeah, regarding problem 5, so I don't know what is the problem, because it is a pretty straightforward thing. So is the doubt regarding the direction of curve cleared, or should I elaborate more? Like, it's just the, I mean, limit of the integration. So you are going from 0 to 2 pi. Yes. Yeah. Okay. Okay. Fine then. If we do not have further questions, so then we will end this session. Okay. Thank you. See you in the next week. Oh, when does, sorry, Riemann means? Okay. So, okay, Riemann integral. So, Riemann integral, so that was done in the real one variable case. So, in this case, we are actually on the 2D plane, and so we are secretly doing a multivariable calculus. So you see, so Z is on the 2D complex plane, right? So we are doing contour integral, so the contour lies in 2D. So it is like we are secretly foliating space in small squares and looking at those, looking at the boundary integrals around those squares. So this is the Riemann integral version in this case. So in the one variable case, we looked at the small intervals, like infinitesimal intervals, and we added all those contributions over all those intervals. Here we look at those infinitesimal squares and add all the contributions from all these squares to get this complex contour integral. So like that is how the, I mean, that is the counterpart of Riemann integral in this case. So otherwise it will not come in the, like they appear in the real one variable case. So yeah. So you can look at Brown and Churchill chapter 4, I guess. So there is some derivation of this Cauchy integral theorem and formula. I guess that will somewhat clarify your concern about this Riemann integral. So that is called the Cauchy-Goursat proof. So yes. Okay, then I will end this session now. Bye. See you next week.